In the next two sections, we're going to learn about how one goes about calculating magnetic fields. Just as we did with the calculating electric fields, where we use Coulomb's law first, and then we found a simpler way to do situations that were very symmetric, namely Gauss's law. We're going to do something similar here. We're going to start off using the Biot Savart law, which is comparable to Coulomb's law in some ways, in that it allows us to calculate any magnetic field produced by a moving charge or by a current. Now, if one wants to find the force for electric forces, it's a pretty straightforward calculation. In fact, we didn't even need to take this step most of the time to calculate the field first, and then from the field calculate the force. We could have just calculated the force directly. But for magnetic fields, it's very much part of the process to calculate the field using the Biot Savart law, perhaps, and then to use that field to calculate the electric force. For one thing, remember, the direction of the magnetic field is not the same as the direction of the force. You have to be very careful. Once you find the direction of the magnetic field, then you have to use the techniques we've already learned to find the direction of the electric force. So let's talk about the Biot Savart law. So let's start off by calculating the magnetic field of a moving charge. We'll do individual moving charges first, and then we'll do it with currents. Moving charges do produce magnetic fields, and the magnetic field is equal to mu naught over 4 pi times Q. Q is the magnitude of the charge, times V cross R hat over R squared. Now the V cross R hat is just giving us the direction that the B field is going to take. So the magnitude of the B field, the magnitude of the magnetic field, would be mu naught QV over 4 pi R squared, and then times the sine of the angle between them, or however you're going to do the cross product. So the direction of R that you're going to use when you're taking that cross product is going to be the direction from where the charge is located to the place where you're trying to find the magnetic field. So we can also calculate a version of the Biot Savart law that we will use when we're talking about currents instead of just individual charges. The same sort of thing we did when we talked about the force on a moving charge caused by a magnetic field, and then we talked about the force on a current due to a magnetic field. What we'll do is we'll take our current and break it up into little pieces. Our current is going to follow a conductor, so we're going to have to break it up into little pieces. But if we have a current that is a little piece of the current, which is I dl, and the radius vector from where that current is to the point where we care about finding the magnetic field is R, and then the magnetic field vector at that point will be, since it's a little bit of the current, a little bit of the length of the conductor times I, the current, then we will talk about a little piece of the magnetic field. And so then, according to the current version of the Biot Savart law, the little piece of the magnetic field is equal to mu naught over 4 pi times I dl cross R hat over R squared again. Once again, it has the inverse R squared dependence, and it has the cross product in the numerator just to give you the direction of your little contribution to the magnetic field. Now, obviously, you haven't taken multivariable calculus yet, at least most of you probably haven't. And so we will not do very complicated integrals. We are just going to try to find situations that have a high degree of symmetry so that we can find the magnetic field using the Biot Savart law just by adding up over fairly uniform segments. So take this example. Let us say we wanted to know the magnetic field at the center of a current loop using the Biot Savart law. So we have a current flowing in this loop. and the direction of the current, it looks like as we're facing it, is going to be going counterclockwise. And so we want to know what is the direction of the magnetic field at the center. Well, so we'll take a little piece of the magnetic field being equal to mu naught over 4 pi times the current flowing in our loop times a little segment of the conductor divided by r squared. And we have to get the direction using the cross product there. Well, looking at that, dl is tangent to that little circular path right there. And the radius vector is towards the center. And as we know, tangents and radius vectors are perpendicular. So by using the right-hand rule, we can readily see that the magnetic field will be coming out of the plane, as it were, along the z-axis. And all of the magnetic fields produced by those tangents to that circle would be coming out, pointing along that same direction. So what we can do is we can just take the entire length of our circle, and so when we integrate over all of our magnetic field pieces, it's just going to be 2 pi r is what we're going to get for the length there. So what we're going to be left with is mu naught over 4 pi times I times 2 pi r over r squared. And if you do the math and cancel out the appropriate things, what you're left with is mu naught I over 2r. So that is the magnetic field in the center of a current loop, and it points outwards away from the plane of a loop. Now, we could, of course, use the same technique to find the magnetic field produced by a current from different current configurations. We could do, for example, the magnetic field produced at a position along the z-axis here that is not in the center of the loop. Pretty straightforward extrapolation from this problem. We could do a similar problem to how we did the line of charge, a short line of charge. We could do a short current, line of current, and then we could even expand it like we did. We expanded the line of charge to an infinite line of charge. We could do the same thing for the line of current. There's just lots of different variations, many of them similar to what we did when we were trying to find electric fields. Because this is only meant to be a review session for you or an introduction to these topics, I'm not going to do them. If you're interested, they are in the PowerPoint available at my online on Canvas.